Okay, good morning, ladies and gentlemen. This is Professor David J. De Los Reyes. What I will be presenting this morning will be a long video format. Okay, this is a topic on dairy current circuit, and we are now on lesson number 4. So, for those of you who are following my channel on the topic DC circuit, this is now lesson number 4. Okay, let's proceed. Our subject matter for this morning will be direct current circuit. Okay. The title of the topic will be a series circuit problem. The last time around, I gave you another topic in which the subject matter was still series circuit problems. So this will now be the second example on the application of the concept of series circuit. The next time around, I will be presenting the concept of a parallel circuit. Okay, that's a different concept. So after this morning, our topic for series circuit will be done. So we will proceed with the parallel circuit the next time around. Okay, I'll try to bring out another problem considering a series connection. Okay, we are given a figure here. This is just a simple problem, okay? But we must have to pass through this one because when we go to the so-called series parallel combination, okay, that will be a harder problem. But at least we know already the concept of a series circuit. That's why I am presenting this example, okay? It's an easy one, but when we go to the so-called series parallel connection, that's a different story. Okay, the figure will be this. We are given a DC circuit, the voltage source is a battery, the voltage is 12 volts. And connected in series, that's why the title of our subject matter is series connection, right? We are given three resistances which are connected in series, and the values are R1 is 100 ohms, R sub 2 will be 200 ohms, R sub 3 will be 500 ohms. This is just a simple one. The problem is just asking what will be capital letter R with a subscript capital letter T, meaning the total resistance of the entire circuit. Capital letter I with a subscript T, meaning the total current. Total current or just simply the common current, because for a series connection, the current is common, right? The current passing through the individual resistances are actually common. Okay, the problem is asking what will be capital letter I with the subscript T, the common current. Next one, capital letter P with the subscript T, meaning the total consumption of the three resistances. Okay, the problem is asking for the consumption. And the last three part of the requirement is that what will be capital letter V with the subscript 1, capital letter B with the subscript 2, and capital letter B with the subscript 3. And what is this capital letter B here? The individual voltage drops on the resistances. Okay, this is B1, this is B2, and this is B3. Okay, the problem is just simple, right? Okay, let's try to bring out the solution to this one using the concept of a series connection. Okay, I place it here, capital letter R with the subscript T, meaning if we try to compute for the total resistance of this entire circuit here, I place it here for a series connection. This is a sigma notation, then next to it is capital letter R, meaning the meaning of this is the so-called summation. Summation of the individual resistances. Summation. Right? That's the concept for a series circuit. If we are to take the resistance of the entire circuit considering a series circuit, The total resistance is just the summation of the individual resistances. Okay, sigma notation R, the meaning of this, summation of the individual resistances. Since there are only 3 resistances which are connected in series, this sigma notation can just be represented by R sub 1 plus R sub 2 plus R sub 3. Substituting values, this is 100 plus 200, okay, plus 500, 100, 200, and 500. The total resistance of the entire circuit will be 800 ohms. As simple as that one. Okay. Next one. If we are to compute for the total current, we have already, what do you call this, computed for the total resistance, right? This is R total already. This is the total applied voltage, and this should be the total current. We have compressed already R sub 1, R sub 2, and R sub 3 to be equal to this R total here. So it seems we are given a simple circuit in which the applied voltage is B, and the total resistance is R sub total, and which is equal to actually 800 ohms as per computation. Right? So if we are to compute for the total current, this will be the equation here. Voltage is the product of current times resistance. So if we are to compute for current, it will be voltage over resistance. I now place the subscript T, meaning total current should be equal to the total applied voltage over the computed total resistance. Okay, so the subscript of the resulting equation will be T, this is T, meaning the total current will be the total applied voltage over R total. And this should be 12 over 800. And this is 0.015 ampere. This is a very small current. And if we try to express this in terms of milliampere, this is 150 milliampere. Right? So the current circulating is 150 milliamperes with the resistances 100, 200, and 500 connected in series. To compute for the total power consumption of the entire circuit, we will be using another relation equation. That is, power is equal to the product of the square of the current times resistance. Okay? So if we are considering the total consumption, capital letter P with the subscript T now will be equal to, I will be placing here, they should be I total quantity square times R total. And this should now be P total, right? This is T, this is T, this is T. Meaning, we are computing for the total power. It should be the total current square times R total. Substituting values, this is 0.015 square times 800. This is a small power. It is 0.18 watts, or this is in terms of milliwatts. This is 180 milliwatts. Okay. Next one. The next one is just the individual voltage drops across the individual resistances. That is V sub 1, V sub 2, and V sub 3. And by using again the equation voltage equal to IR, okay, we could compute for the individual voltage drops across each resistance. This should be V sub 1, V sub 2, V sub 3. So if I will try to compute for V sub 1, V sub 1 should be V sub 1 should be I sub 1 square times R sub 1. But this I sub 1 is actually I total quantity square, because the current is common, right? I total is the same as the current passing through I sub 1, same as I sub 2, same as I sub R sub 3, right? Because the connection is series. So this should be 0.015 square times 100. The voltage drop across this 100 ohms here is actually equal to 1.5 volt. Right? Again, by using the same formula, B sub 2 now will be equal to I sub 2 square times R sub 2. And again, this I sub 2 is same as I total, quantity square. The current is common, right? So this should be, no. There is no power, sorry for that one. It will just be simply I total. I1 R1, right? Sorry for that one. Okay, 0.015 times 100, that is 1.5. Next one, what do you call this? I'm thinking of power, right? Voltage is still I sub 2, R sub 2, and this I sub 2 here is same as I total, right? Sorry for that one. So it should be 0.015 times 200, and that will be 3 volts. So the voltage across this R sub 2 here is actually 3 volts. And again, for V sub 3, this should be equal to I sub 3 times R sub 3. But this I sub 3 here is actually same as I total. Right? So the current will still be 0.015. The current is common, times 500. The resulting voltage V sub 3 will be 7.5 volts. So this is with the value 7.5 volts. I think requirement B sub 1, B sub 2, and B sub 3 is just a check if the total voltage is actually same as equal to the summation of these three voltages here. So as a check to the validity of our answer, this will be our answers, right? 1.5, 3, and 7.5. And as you check, for a series connection, the total voltage across the circuit is just the summation of the individual voltages. This is actually same as the sum of B sub 1 plus B sub 2 plus B sub 3. Okay? The total applied voltage is 12 volts. Okay? And is it equal to the summation of the individual voltages? Will it be equal? For a series connection, it should be equal. So this is 1.5 plus 3 plus 7.5. The left hand side is 12. The total applied voltage is 12. And the summation of 1.5 plus 3 is 4.5 plus 7.5, that's 12. So what comes out, if we try to check the validity of the answers B1, B2, and B3, what comes out is 12 is equal to 12. It is true. So our answers are actually B1 equal to 1.5, B2 is 3, and B sub 3 is 7.5 are actually correct. Okay, that's it, guys. Series connection is just a very simple, concept. But when we go to the series parallel connection, that will be another story. But at least we know how we compute problems under series connection, because when we go to the series parallel connection, we will be using some concept of series maybe, and we will be using concept of parallel. Okay, so it's a complicated thing, but at least we have passed by the concept of the series connection. Okay, that's it, guys. So for those of you who are following, who would like to watch my videos on my long video format, my channel is at youtube.com/@ProfDavidJ. If you want to share it, please click share. I am assuring you, you will learn something from it. Okay, good morning from Los Angeles, Professor David J.